Okay, so what I want to help you out with is balancing redox equations, okay? So I'm looking at the handout that you were given in your second Head Start lesson called Electrons on the Move, Redox Equations. Very interesting. Some of the questions in here are really tough to get. So I'm going to take you through two of them to show you how to deconstruct these equations, so pull them apart to get the half reactions, and reconstruct them, so using the half reactions to get the full balanced redox equation. Okay, so you have to know two things here. You've got to know about assigning oxidation numbers, and you've got to know how do we balance redox reactions. Okay, so first thing I'm going to go over, I'm not going to go over oxidation numbers yet. I'm going to do that as we look at the actual reactions, okay? So I want to talk about the Coe's method, okay? Some people call it the Coe's method, other people just memorize how to do it. But if you're interested in balancing redox reactions, you've got to know what these things sort of mean. So the first thing is you balance the key element, okay? So things that aren't oxygen or hydrogen. And you balance your oxygens by adding water, and you balance your hydrogens by adding positive hydrogen ions. Finally, you balance your electrons by adding electrons to either side of the equation, and it's always good to remember that you add the electrons to the positive side of the equation, to the more positive side of the equation. Okay? And then finally, the S in there is meant to remind you, don't forget your states. Okay? So let's have a look at one of these problems. Alright, so this is problem B from your worksheet, and I've just cut it out here and put a picture there simply because, unfortunately, on this program I can't get superscripts or subscripts. So I'm going to have to write them out, and it'll look a bit daggy, but I hope you'll get it in the end. Okay? So even before we start to sort of write the reduction and oxidation half equations for this thing, what you should be thinking about here is oxidation numbers. Okay? So I usually write them, and you can see I've done it on my question there. I've written them in a different color just over the top of the elements. You can write them over top or on the bottom, but just make sure you can, it's clear so you can read it. Okay, so let's start first. Okay, oxidation number. So let's start with the first species in the reactant side. Okay, so we see oxygen there, and we know that it's not a peroxide. And oxygen that's not in a peroxide form has an oxidation number of -2. Okay, so we've got 4 oxygens with oxidation number -2, and the overall species has got to have a charge of -2. So that means our sulfur needs to have an oxidation number of +3. Okay, let's go to the second species there, water. Again, oxygen has an oxidation number of -2, which means that hydrogen has got to have an oxidation number +1 because the overall water molecule is at neutral. Okay, and we're going to go to the first species in the product side. Again, easy peasy, oxygen's got an oxidation number of -2. That species has an overall charge of -2. So sulfur has got to balance out that -6 contribution from the oxygen in order to give a -2 charge on the molecule. And for this to happen, sulfur's got to have an oxidation number +2. Okay? Finally, our last guy in the products. Okay, oxygen has an oxidation number of -2. Hydrogen has an oxidation number of +1. And if you do your algebra, you can pause the video at any moment to do that, you will find that sulfur has an oxidation number of +4. Okay, so maybe you want to pause it, check to see if you can get the same sort of oxidation numbers that I've got, alright? But if not, don't worry, we'll move on. Okay, I'm just going to change the color of the pen here. I'm not sure if you can see me doing this. So what I usually do now, even before I start writing my reduction oxidation numbers, I say, oh, hey, look at this. Sulfur began with an oxidation number of +3, and it goes to an oxidation number of +4 in one species, and it has an oxidation number of +2 in another species. So I get thinking to myself, okay, going from a lower oxidation number to a higher oxidation number, so we're talking about a loss of electrons here, and we're talking about oxidation. Remember your oil rig, if you like to remember it that way. In the second part, going to a smaller oxidation number, so which means a gain of electrons, so we have a reduction happening there. Okay, so let's begin writing the reduction oxidation half equations. Okay, so what I've just done is I've just set us up to look at these half reactions and then begin to balance them. So what I did here was I said, okay, for our reduction reaction, I've started out with this species here, and it's been reduced, and now it's in this form here. And the same thing for our oxidation reaction. We start out with this species, and we move to that species. Okay, so let's go up and look at our Coe's method to sort of look at how we're going to form these two half reactions. I'm just going to change the pen color again so that you can see what I'm adding there. Okay, so we begin with the K, so the key elements in the reaction, so the elements that aren't oxygen or hydrogen, and we can see that for the reduction reaction we've got 2 sulfurs on the reactant side, 2 sulfurs on the product side. Boom, we're in the money. Those are balanced. Let's go to our oxidation reaction. 2 sulfurs on the reactant side, but only 1 on the product side. So what we're going to have to do is I'm going to have to add a coefficient of 2 to that side of the equation so that I get 2 sulfurs there and 2 sulfurs there. Okay, done. Let's balance our oxygens now. Now to balance our oxygens, we need to add water. So I've got 4 oxygens on the reduction reactant side and only 3 oxygens on the reduction product side. So I'm going to have to add a water molecule, H2O, and I'll just put a plus in there. Okay, so that means we've got 3 plus 1 oxygen is equal to 4. Okay. Now on the for the oxidation reaction, on the reactant side I've got 4 oxygens, and then it's a bit tricky. I got fooled by this many times before. We've got 3 oxygens there, but we have to remember the coefficient in the front. Okay, so 2 multiplied by 3 is 6, so in total we have 6 oxygens on this side, but only 4 on that side. So I'm actually going to have to add 2 water molecules to the reactant side of the oxidation reaction. Okay, so now we've got 6 and 6. All right. Then we go to balancing our hydrogens. So what do we do to balance our hydrogens? We look to see which side there are more hydrogens on, which in the reduction reaction happen to be the products, and we need to add some hydrogens over here on the reactant side. So I'm going to add, because I've got 2 hydrogens on the product side, I'm going to add 2 H+ ions, so hydrogen ions, onto the reactant side for the reduction. And then onto the oxidation, I've got, remember, don't be fooled by the coefficients here. 2 times 2 is 4 hydrogens on this side, but we only have 2 hydrogens on the product side. So I'm actually going to have to add some more hydrogens over here. So I'm going to add 2 of them, H+, okay, over there. All right, we're getting there. Now comes the kind of confusing part sometimes, adding the electrons, okay, so to balance the charge. So what you can do is look over on the reactant side, -2 plus 2 times +1. So actually this side of the equation has a 0 charge. But over here we see that on the product side it's got a charge of -2. So we're going to have to add 2 electrons to the reactant side of the reduction equation. Okay, right, let's go over to here. Okay, on to the oxidation reaction, we can see that we've got a -2 charge on the reactant side, and then on the product side, well, we've got 2 times +1, that's +2, plus 2 times -1, that's -2, so that works out to be an overall charge of 0. So we have sort of the opposite happening. That makes sense. I'm going to have to add 2 electrons over here in order to balance the charge on this side with the charge on that side. Now this is where we say, awesome, this is wonderful, because we've actually seen that our electrons are on the opposite side of the equation. So if we would actually go back up and try to get the overall equation, we would see that these 2 equations added together would cancel out these 2 electrons. Coincidentally, they cancel out the hydrogens and one of the waters, which is exactly what we want. Now, this is a very messy slide, and we can see that I'm not going to exactly finish the S bit, on this slide because it's quite messy. So the S in the Coase method is just meant to tell you, hey, don't forget your states, which is a very, very common mistake for high school students to make. All right, so let's see, what do we come up with? Okay, this is what I came up with. This is my work here, and the reason why I haven't written it down for you using my finger on the iPad is because it's going to turn out messy. So I can read it out for you if you like, or you can just pause it and have a look at it. All right, so what we have is we've got the reduction reaction up here and the oxidation reaction on the bottom, and you can see these little squiggles here mean AQ. Okay, water in the liquid form, AQ again, water in the liquid form. Now, I said to you before we should be really happy because if we added these two equations together, chemistry is kind of like math. If we add them together, we can see that our hydrogens cancel out, our electrons also cancel out, and so does one of our waters. Okay, and if you actually do this, you will see, if you can maybe write down your answer there, you will see that we get the original equation in the end. So in fact, I love doing these problems because you can actually check your work in the end and say, well, did I actually deconstruct or take apart this equation to get the half reactions in the correct way? And you can see that you actually have. Okay, let's move on to the second problem. Okay, so this is question D on your sheet, and I've taken a picture of the actual question, and I've mucked it up a bit because I don't want you to see the answers before we actually go through it. All right, so what this question is asking you to do is it's saying, okay, dude, identify the reduction half equation and the oxidation half equation, and then what they want you to do is they want you to actually construct the overall ionic equation for this. Okay, so let's do it together. Pause the video at any time you want, all right? So what I'm going to do is I'm just going to work on this page, and I'll hopefully show you, hopefully it'll be clear. I'm going to change the pen color just so that we can write our oxidation numbers in. Okay, so firstly we've got this thing up here in the reactant side of one equation, Cr2O7 -2. That's actually the dichromate ion. Okay, fun. Now let's assign oxidation numbers. So -2 for oxygen, because it's not in a peroxide form, and in order to get an overall charge on the dichromate ion of -2, that means chromium is going to have an oxidation number of +6. Okay, over to the reactant side of this equation, fantastic, easy peasy. Chromium's already got its oxidation number written as a charge, which is +3. So one thing that we should be taking home from this is we should be seeing that, okay, we've got a decrease in oxidation number, so we're having a gain in electrons. So I'm just going to label that already reduction. Okay, it's gain in electrons. Let's go to the second equation here, C2H6O and C2H4O2. Okay, let's start with oxygen again. -2 oxidation number because it's not in a peroxide. Hydrogen will always have a +1 unless it's in a hydride, which it's not here. And in order for this molecule, whatever it is here, to be neutral, our carbon is actually going to have a -2 charge. Bizarre. You don't often see that. Okay? Well, it's not actually a charge. It's an oxidation number, so I shouldn't be telling you the wrong thing, I guess. Okay, so let's go over to the product side. And we've got oxygen again with an oxidation number of -2, hydrogen with an oxidation number of +1. Okay, that whole thing there has an overall neutral charge, so it doesn't have a charge at all, and that leaves carbon with an oxidation number of 0. Okay, so one thing that you should be taking home here is, hey, carbon goes from -2 oxidation number to an oxidation number of 0, so it's losing electrons, and we are having an oxidation. Okay, so there's our labeling. The first reaction is a reduction reaction, and the second reaction is an oxidation reaction. And that makes us very happy because we know that reduction and oxidation always happen at the same time. Awesome. Okay, so now what we need to do is we actually need to balance these half equations. Okay, and I'll take you to another slide in order to do that. Okay, so here we are. All I've done is I've taken the question and separated it into the two reactions that we made conclusions about earlier. And let's balance it using the Coe's method, okay? So first, the K standing for, all right, the key elements. So in this case, in the reduction reaction, we've got chromium that we need to balance on both sides. Just change the pen color so you can see what I'm doing. Okay, so we've got 2 atoms of chromium on the reactant side and only 1 on the product side, so we're going to have to add a coefficient of 2 in there. All right, let's have a look at the oxidation reaction. Our key element is carbon. Oh, how good is that? We've got 2 carbons on the reactant side and 2 carbons on the product side. Fantastic. Nothing we need to do there. Now let's balance our oxygens, and we balance the oxygens, remember, by adding, yes, water. Okay, I hope you said that. So on for the reduction, on the reactant side, we have 7 atoms of water. So we need to add plus 7, sorry, not 2, 7 molecules of water to the product side. Okay, over on the oxidation reaction, on the reactant side, we have 1 atom of oxygen, and we have 2 atoms of oxygen on the product side, so we're going to have to add 1 atom of oxygen to the reactant side, which means adding 1 water molecule. Okay, hope that looks good. I think so. And then let's go on to the next one, balancing our hydrogens. So we can see, don't be fooled again, we've got no hydrogens on this side in the reduction, but on the product side we've got 7 times 2, that's 14 hydrogens, so we're going to have to balance it on this side by adding 14 hydrogen ions. Okay, let's go over to the oxidation reaction. We've got 6 hydrogens plus 2, that equals 8 hydrogens on the reactant side, only 4 though on the product side, so in order to get that equal, we're going to have to add 4 hydrogen ions to the product side. Okay, good. We're almost home. Electrons. Okay, now be careful. Remember our coefficients here. So 14 times positive 1 is plus 14, plus negative 2, that's plus 12 on this side, and we've got 2 times positive 3, that's plus 6 on this side. So we've actually got a higher positive charge on this side than we do on the product side. So we're going to have to add there plus 6 electrons. Okay, let's go to the oxidation reaction. Ah, great. 0, 0, no charge on this side of the equation, but oh, we've got a whopping plus 4 charge on this side. So what we're going to have to do here is add plus 4 electrons to that side. Okay, so I'm going to not worry about the states right now. Let's think about that later. And let's see, I wonder, is this looking all right? Well, we've got electrons on different sides of the equations, but we've actually got different numbers of electrons. I wonder how this is gonna work out. So we've got our balanced half equations here. Let's take a look at actually adding them together to get the full redox equation. Okay, and what I'm going to do is I'll take you to another slide for that. Okay, here we are. I'm not going to delete anything from this. I'm showing you my actual work here. Okay, so what I'm going to do is I'm just going to explain this to you, and if you want to write it down, you can pause at any time and have a think about it. All right, so we've just got exactly what we did before. Okay, I'm just drawing a square around it there, with our reduction reaction and our oxidation reaction. Okay, now remember how I was saying that, oh, we've got different numbers of electrons on either side. Well, in order to get the full oxidation reduction reaction, what we do need to do is we need to multiply those by common factors in order so we can cancel these guys out. Okay, and that's what I've done to get the final equation under here. So I'll read it out to you if you can't read my messy writing. We've got 2 dichromate ions in the aqueous state plus 16 hydrogen ions also in the aqueous state plus 3 C2H6O, whatever that is. That's kind of weird. I prefer a structural formula there, or a semi-structural formula, but anyway. And that's producing 4 chromium 3 plus ions in the aqueous state plus 11 water molecules there in the liquid state. Okay, so that's it. You know, it's balanced. You can check it again if you like. and that's the end of the problem, but you might find this kind of interesting. This reaction here, this redox reaction, you can find that in a breathalyzer test. Okay, so if you have drunk too much, and this guy here is ethanol, if you've drunk too much ethanol, and I'll write that CH3COH, so you can kind of see what that thing looks like. If you've drunk too much alcohol, which has ethanol in it, you breathe in, and that ethanol that's on your breath, it goes through this reaction and tells the police that you shouldn't be driving. So, hey, food for thought there in year 12, I guess. Thanks very much. Tune in next time.